And awesome sauce. So, hi everyone. Thank you for joining our last session for our pre-hackathon workshops. I know students are slowly trickling in, but you know what? We have to keep the ball rolling because this is a lot of important information that you will hear within these 2 hours. Um, so as we know, my name is Amanda. I'm the experiential learning coach here at LaGuardia Community College. And I'm sure somebody just emailed me. Thank you again for coming to these pre-hackathon workshops. I am going to introduce Nate, and then Nate can introduce everyone else. I had a pleasure of meeting Nate a couple of weeks ago, and I shared with him that, hey, I need help with the hackathon. Can you please help with some pre-hackathon workshops? He said, sure. I have this concept, I have this idea. Can we run it with your students? I said, why not? Right. So I am going to, this is Nate's show, Nate and Company show. I like this for right now. And I'll have Nate introduce everyone. And guys, feel free to ask all the questions, put it in the chat. This is being recorded, so we will share this with students who were not able to make it. Again, you can be able to utilize these tools for the hackathon, which starts tomorrow. So please keep your ears open. And I'm so excited. Nate, the floor is yours.
I feel like I should have had a top hat since it's my show. Hi, I'm Nate Cooper. I'm appearing in kind of a dual role that my two lives. I run a company called Swarm where we do product design, but I also teach UX at Kingsborough College and sister of LaGuardia, so we're in the family. So Mike Caprio is a good friend of mine. We've worked together for decades, and he got me interested in this hackathon called Space Apps. And last year I hosted Space App. This is NASA's Space Apps Challenge. It's hosted every year as a global hackathon. And I was the local lead last year and hosted a sort of a local site at Kingsborough College. And that hackathon is it's all about integrating kind of science data and technology solutions. Now, coming from the world I'm in, where I'm sort of a design technologist, I have a super interest in science and space and cool things like that. But I asked Stephen Jaret, who's a colleague at Kingsborough, to help as a science advisor. So really the hackathon came together really by sharing those resources. And so this event today, this webinar kind of grows out of that collaboration. We're working with Mike, and Mike recruited Patrick to kind of, further the mission of like doing cool stuff with science data is the way I'd frame it, but there might be more technical terms that people throw around. I'll let everybody introduce themselves and give a little bit of their background. I'm here to kind of be a facilitator and chime in and maybe help with some context, but please, the floor is really turned over to these fine people. I'll go ahead and turn it over to Mike, and then Mike, you can pass the mic along.
All right, fantastic. So welcome everybody to this webinar. I hope all of you have a really exciting experience at your hackathon tomorrow. And I hope that what we're presenting today will give you a little bit of insight into a very broad topic of categories. We only have a short time to dive into it today, and especially since you're getting into it tomorrow. But we will try and give you a sense of how one can use scientific data or really data of any kind, which can be accessed through APIs to be used in hackathon projects. So my role, so I work at the Tesla Science Center at Wardenclyffe. I also do work with Nate on his agency projects. I'm a freelancer, a consultant. I worked for 5 years at the American Museum of Natural History, helping them with hackathons and research innovation, working together, bringing technologists, collaborators together to work with their research scientists and staff. I also was a founder of the NASA Space Apps Challenge in New York back in 2012. So Nate's kind of picked up the torch for that, I think, for New York City now that we're out of pandemic and back to having in-person events again. But we're going to present to you a bunch of really cool data today. And I brought Patrick Morgan, who is a great STEAM educator and instructor, computer scientist himself, and very passionate about open data. and about using it for making life better on Earth and in space, as is the Space Apps charge. Stephen's also at American Museum of Natural History, so we'll be presenting a bunch of interesting space-related and scientific-related data. But I'm going to bring it on to Patrick, who will be presenting next.
Yeah, thanks, Michael. I'm going to go ahead and share or take over the screen here and start sharing. Could I verify that we all can see the first slide?
Yes, and I see your mouse as well.
Okay, great. As I move this around and get ready to begin here, this will be a rather high-level overview of open data and the impact that it has on ourselves, both as computer scientists, as Michael mentioned, but then also just as people and as Americans and as users and consumers of data. I'm specifically going to be talking about APIs, a little bit about climate science, how I'm involved with that in the real world, and then how I can bring that to help you all with your hackathon. And then also talking about just creative applications in general, maybe some applications that we're familiar with or some applications that we're not so familiar with that will aid us in our process of this data exploration. So as mentioned, my name is Patrick Morgan. I build machine learning and software tools that help make complex climate data more easily understood. Right? At the very basis of what I do, I take complex data and I make it more easily understood. For who? That could be a range of different people. It could be for a startup building some software use case around the data. It could be a public institution such as a library or a hackathon or a college, or it could be a nonprofit. Anything that is at the intersection of risk assessment, climate capital investment, conservation, and technology, that's pretty spot on to where I fit into the picture. Today's session, as mentioned, is designed to give you an applied, very fast-moving look at how open data, especially data from the government organizations NASA and NOAA, can be used in real-world projects and hackathons. There'll be a lot of acronyms and a lot of external information that you might not be familiar with, but we'll provide that all to you afterwards, not only in a recording of this, but I think we're going to send up a web page with some of the examples that I go over, or any of the tools and technologies that I mention, and any of the tools or technologies that I end up showcasing. We'll be sure to link all of you so that you can explore on your own or interact with on your own, even for this upcoming hackathon. So the things that we're going to be covering today cover and range from basic data workflows to the process of finding meaningful data sets. Where do we find them? How do we decide if a data set is meaningful or is useful for the project that we have in mind or the idea that we have in mind for? And then what is downstream for that? What's downstream for that data? So how do we ingest the data? How do we clean it? All different types of terms that are going to go along with that entire process. So we really want you to go from what's out there and what can I build to, or excuse me, I really want you to go from what's out there and a general understanding of what is out there to what you can build as quickly as possible. So that's hopefully going to be through our examples today. And that could be from building a map, a dashboard, an alert system, things that we're going to constantly talk about as more concrete examples as I present. After that, I will hand it back to both Michael and Stephen, who will walk you through some of their specialized climate visualizations and space data, which should be a really cool way to end our session. If you have any questions, please feel free to drop them in the chat. I would think that that's probably the best way to get them answered quickly, as we have Nate, Stephen, and Michael will be overseeing the chat as I sit up here and speak a lot. I'll try to stop and answer any questions maybe every few minutes. But then we'll also have some time at the end of both my presentation within the next hour or so, where I'll stop and answer some questions on what I was speaking with, and then we'll also do a question and answer session at the end. So without further ado, let's go ahead and get started, because I do not have that much time, so I will be speaking and moving a little bit quicker than normal, at least for our cadence and our pace. And we're going to be starting with our data exploration. So as I continue to mention this process that we're going through, this process is shared by, is a common workflow for interacting with data, right? And the first step of that is data exploration. So we see a quote here from Tim Berners-Lee, one of the inventors of what we know as the modern World Wide Web, talking about how data is a precious thing and will last longer than the systems themselves. I've included some quotes by some other famous computer scientists and business moguls that will hopefully add some context to what we're doing along the way. Our agenda is going to begin with a short overview of why open data matters. So not just in theory, but also in practice. Like especially in a world where public science is increasingly vulnerable to censorship or even deletion. And we're going to walk through a lot of the key technical ideas of how APIs work, what ETL, the acronym, means. It stands for extract, transform, and load, in case you were wondering, but we'll dive way deeper into that when we get to that section. And in terms of data pipelines, how do we think about structured versus unstructured data? What's the difference between them? How do we gauge when something is unstructured versus unstructured, excuse me, and then how do we interact or ingest that type of data? After that, we're going to show you where to actually get this information, where on the internet, where in, say, maybe the context of the real world, maybe like if you're working on the job where you can get information. And I'm going to be focusing specifically on climate and satellite data, as mentioned from both NASA and NOAA. Government organizations, scientific government organizations that you might have heard of, aka NASA, and maybe that you haven't heard of, but that are almost guaranteed involved in your daily life, such as NOAA. You can access this data, once again, for free. They're open to the public. They are used by people all over the world, from scientists to computer scientists to almost anyone in between. Finally, we will walk through some actual examples. I'm hoping to get through at least one example, but I have 3 or 4 in here that we can go through if we have some time, where we will be fetching real-time climate data from a NOAA API. Specifically, I'm going to be walking us through some daily temperature summaries, very low-hanging fruit, very easy to understand and very easy to visualize data using a Python notebook of sorts, which we'll also talk about what that is. It's really a fast, practical workflow that you can certainly repurpose during your hackathon time. As mentioned, at the end, we'll transition to Stephen's demo, where they'll be exploring 3D visualizations using NASA's OpenSpace suite. The first section that we're going to be going over is preserving access to science, why open data matters more now than ever. So before we dive into the tools and the APIs, I just want to start with something very fundamental of why open data matters and why preserving public access to that data and to science in general is incredibly urgent and personal. This isn't just a technical topic. In recent years, we've seen federal websites taken offline. We've seen tools removed from public view. Scientific teams have been dismantled for political reasons. Publicly funded science meaning data from satellites to climate forecasts, is more vulnerable now than it ever has been, certainly in my life, and certainly in recent memory here. And when this is vulnerable to deletion, restriction, or even distortion, that can have very serious impact for not only the future of our learnings, but it can also have a direct and immediate impact on things like the economy, which we're going to be seeing very recently in real time here. Because this data doesn't just fuel innovation, right? It protects the truths, right? It protects the truths of our past, of our past history, and of our past in general. So I believe that it's up to all of us to ensure that it remains accessible, especially during moments when truth itself is under pressure. So why is data important, right? A rather trivial question that has some really large implications, because data powers everything from the insights and innovations across industries that we're used to enabling smarter decisions that impact things from the personal choices that you do daily to large-scale global challenges. So when we're thinking about data, we want to think about it being crucial for making informed decisions in every field, right? It's very important to note that data is used in almost every field that you're aware of, and probably some that you aren't. So it helps individuals and organizations analyze those patterns and make predictions and act based on facts rather than assumption. So an example in healthcare could be that doctors use data from patients' medical records, say blood pressure, heart rate, medical history, to diagnose diseases and recommend treatments. What about in science, right? There's examples, we talk about NASA, or I've mentioned NASA a few times. NASA uses data from satellites and space missions to study climate change, track changes in Earth's atmosphere, and predict future weather events, specifically extreme weather events, which are happening more and more often nowadays. This satellite data helps scientists understand how Earth systems interact with each other. So there are some more specific examples that we can go over. For instance, NASA's PACE program, which tracks ocean color and monitors phytoplankton levels, studying the effects of marine ecosystems. So what about for businesses, right? We know that business analyze customer data, right? Almost every website or app that you use, you have to abide by some form of data collection nowadays, whether it's cookies, if we even know what cookies are doing to us, or really long terms and conditions that aren't often read, right? We are giving businesses access to our data, actually unprecedented amount of information on ourselves. And that could be purchase history, your general online behavior, whatever it may be. Those businesses and businesses in general use that data to improve marketing strategies, develop new products that cater to specific consumer preferences, right? To cater to specific groups of peoples or use cases. So we can think of Amazon using customer purchase data to recommend products tailored to our preferences, right? I think that's a very easy example. Or maybe something like a Netflix or a Spotify recommending a new song or a new show based on what else you've used. Some other examples, we must not forget that the government, especially where we live, like government in general, is a big creator and user of data, right? So they not only create lots of public data, but they use data to make decisions about public policy. They monitor things like unemployment rates, managing budgets for local to state to national principalities, right? Tracking the spread of diseases. If we all remember COVID-19 or SARS, which is maybe a little bit older. When I was younger, I know that was a really big deal. Or even like the H1N1 flu going around right now, right? And tracking that against egg prices. So just to say, there are many different use cases and there are many different versions of data, and they are important to us in almost every layer of our life. I think I read a report the other day that said 90% of Americans use publicly funded open data on a weekly basis. And I was thinking that that was a very low number. I was thinking it'd be higher 90%, and I think it'd be on a daily basis. So let's think about that percentage as I move through these sections. Once again, do 90% of us, so do you think 9 out of 10 people you know use public data? As we go through and as I provide some more examples of what that may entail, let's see if your thinking or your thought process was correct with that, right? 9 out of 10 people you know using public data. So when we're talking about open data and public data, I think it's really important to talk about right now the context of preserving science in the face of censorship. So since 2016, the US specifically has seen large-scale removal or suppression of climate science from public infrastructure. So we've been seeing over 50,000 federal science and climate web pages have been deleted, altered, or crucial resources moved around only since November. So in about 6 months, right, about 100 days, we've seen over 50,000 web pages be deleted or altered to include confusing or just false information. And some of the websites that have been deleted, the majority of them are for climate-related information, but also health-related information, and then also risk assessment. Lots of like FEMA's websites used to have risk assessment tools, which would give you future risk indexes that were used by everyone from insurance companies to travel agencies, right? So other things that were taken that have been taken down are websites on sea level rise, wildfire risk, emission data. There have been tools that help communities plan for floods, fires, storms. All of those have been taken down recently, and we'll talk in a moment about like what we're doing to combat that. But also, we've seen large-scale dismissal of scientists, removal of publicly funded grants for science, specifically around anything to do with climate or DEI or activism. We've seen scientists at the National Climate Assessment, which is something that we give out to the entire world every year. And lots of people use it lots of other people in the world use it to base their research on, to base what they're going to do for the next year, to abate risk for wherever they live, based on some of the information that the United States has given out over time. So what's happened, or what's been happening in the face of this, has been a large-scale concerted effort by the public. So we've seen a response from everywhere from librarians to researchers to activists to climate activists to nonprofits to software engineers and just about everyone in between, doing large-scale grassroots archiving efforts. A few examples of them would be the Data Refuge Project, the End of Term Archive, and then also the Public Environmental Data Partnership. The PEDP, Public Environmental Data Partners, is something that I will be sharing a link to and that I've been working with over the past 2 months. We'll be sharing links to the data and tools that they have been archiving. Some of the larger ones that have went up recently include the EPA EJ screen, which is a screening tool for housing locations for air quality. Also the Climate and Economic Justice Screening Tool, also known as CEJST. And then also, as mentioned before, the FEMA Future Risk Index homepage and tool. The Department of Education also had a local investment map. That is another one that we have been working tirelessly to get back up on the internet. We will provide, once again, links for that. In those links, there's not only lots of information on open data, where you can find open data, where they're finding open data, but also if you're looking to get involved and if you're looking to help archive some data, these are some great jumping off points for that. We have to remember that open data is not just a convenience for us scientists, but it really is a line of defense, right? When science itself is threatened, and the access to that information becomes its own form of resistance, right? So as developers, as researchers, as builders, we are part of the defense. And for me, it's been very important to continue that advocacy in the face of the deletion of this information. So here is actually the link to the screening tool. Maybe I can throw that in the chat. I don't think that I can enter any information into the chat, but if we could, Michael, if you wouldn't mind putting that link, screening.tools.com, into the chat for everybody, that would be very helpful. Thank you. I will pause to see if we have any questions here before I move on to our introduction to data section. I'm not seeing anything right now, so let me just move on. Let me continue moving because I do have a lot to cover. In this section, I'm going to be talking about the who, what, where, and why of data. I've included some videos in this section, but we're not going to have time to watch them right now. So please go ahead and we can either watch them at the end if we have any time, or we can add these links to the webpage as mentioned for later. Great. So before we were talking really in general of just exploring data, where do we find them? As mentioned, there's free resources supported by the government. There are also some other places that we'll showcase. But let's talk about the collection of data, right? If we think about, okay, we find this data online. Now we're going to go through an entire history of data, right? The anatomy of data. So it starts at the collection step, right? So there are different ways in which these organizations collect data. Firstly, there are satellites. So satellite data can include optical sensors. So that means they could capture visual images, something like a camera. That would be good, or that type of data would be good for tracking changes over time, right? Think about the shrinking of the polar ice caps, right? So some spatio-temporal data that compares pictures from 1990 to now. We'd be able to see differences in not only polar ice caps, but how about land use and land cover of, say, tree cover for any given forest, or for the Amazon, or for if you were a farmer and wanted to know how the land around you was being changed over a long period of time. That's where optical sensor information would come in, or data. There's also radar sensors. Radar sensors are good because they can see through clouds and darkness, meaning that we could capture, we could detect things that you wouldn't be able to just from a surface picture. Maybe ocean wave patterns, right? Or ocean currents, or anything within the ocean, or anything that would need to be analyzed deeper than just a optical or a sensory picture. And to expand upon that, we also have infrared sensors, right? So infrared sensors measure heat emitted by Earth, which seems very straightforward, but you can monitor so much with that. You can monitor temperature changes. That way you can track wildfire potential, urban heat island effects, right? Anything to do with temperature that you may think of. There's also ground-based sensors and data, and airborne as well. So on top of there being ground-based sensors, I know here in New York City are some of the oldest ground-based sensors for weather almost anywhere, but like they're definitely the most active, the most constantly used ground-based data centers in America are still here in Central Park. They give us all types of weather data every day, and you can really go visit them. Every once in a while, they have tours throughout them for the New York City Parks Department, specifically around fall and around Climate Week. There'll be lots of different informational events on the data that we collect here in New York and how we do collect it. So besides the collection of data, it's also going to be important. It's also going to be important for us to just give some general examples of the types of data, right? So not only do we collect them from multimodal or multi different ways to interact and collect data, right? We've got satellites, we've got land data, we've also have ship data, right? Boats have tons of data collection on them, or we can drop buoys into the ocean. On tops of planes, we also use weather balloons quite frequently still now, which I know often surprise people. But so when we're talking about data, there's a few different types of data that we want to be speaking about, right? So remember, we're keeping this very general, very generalized right now. In terms of structured data is easily organized, easily searchable information, often stored in table format, right? So that means rows and columns. So any spreadsheet that you're familiar with, Excel's, Google Sheets, a SQL database, a financial record, or any type of inventory list would be an example of structured data. We can also think of, in terms of climate data, a weather station could record daily temperatures, wind speed, humidity. If each of those data points were neatly structured into columns for easy analysis, then that would be structured data. And this is used, right? Meteorologists gather structured data from satellites, from sensors, from ground stations, and forecast the weather using information such as temperature, precipitation, wind speed, all recorded in a structured format. The weather apps that you use on your phone that are telling you the daily forecast, they use structured data from weather stations, but more importantly, they use publicly available weather information from the government. So every single weather forecasting application out there, any single one, and specifically any one that you have on your iPhone or an Android phone, uses publicly available government data, specifically NOAA data. And I don't know if you've noticed, but recently I've noticed that weather forecasting has not been good. I've noticed recently that the forecasts have not been accurate. The timeframes have not been accurate. Sometimes it'll say this big storm's coming in 3 days and it comes the next day, or the opposite. That is happening right now, right? So with the removal of these scientists, with the defunding of these programs, the accuracy of our information has went down, and it's went down quantifiably in a way where we can measure that it is less accurate and that it is less real time and is less up to date. So there are real world implications for the for having access to this type of information. So on the flip hand, other than structured data, we also have unstructured data, right? This is information that doesn't have a predefined structure, usually making it harder to process or to analyze. So if structured data was the weather data that we're getting, right, very structured, temperature, precipitation, latitude, longitude, time, then unstructured data from that example would be What about social media posts about a storm, right? The text from those social media posts, emails, images, videos, audio recordings of a storm, those would all be considered unstructured data, right? They don't have the connections and the correlations between different points like structured data does. The next distinction that we want to make is the difference between data and information, right? So data is going to be the raw, unprocessed facts, figures, and statistics, where information is the data that's been organized, processed, or interpreted in a way that provides meaning or value. This slide is very important. If you can use, or if you think of a, what is the purpose of my quick 45 minutes with you? It's to outline a structured approach to interacting with data. And one of that is going to be going from data to information. And in the real world, that's what you should think of as well. How do we go from a raw, unprocessed amount of facts and figures to an organized, meaningful, valuable amount of information that I can then process, right? So we want to go from data to information. Data on its own doesn't have much meaning or relevance until it's processed, until it can be in various forms such as numbers, text, images, symbols. So let's give an example here. So an example, a list of temperatures recorded over several days: 25 degrees, 30 degrees Celsius, 28 degrees Celsius, 40 degrees Celsius, or Fahrenheit. It's been pretty warm here, 70, 72, 74. That is just data. It is raw, unprocessed information. So until someone organizes, processes, and interprets that to mean value, so until we run an analysis that shows the average temperature over a week or shows an upward trend in temperature over time, then that is when it becomes information. So let's keep that in mind as we move towards some quick data types here. So there are digital and physical data types, but we're going to want to think of 4 different types. We're going to want to think of numerical data, categorical data, textual data, and then geospatial data. So numerical, that's very straightforward. Numbers often used for measurements or calculations. Categorical are going to be groups or labels, with textual being written forms like reports, sensor readings, research papers. Those can be either in digital or physical formats. And then we have geospatial data, which is tied to a specific location, often visualized using maps or satellite images. I'm going to continue moving quite quickly through here so we can get to some real world examples, but there's also ways that we organize our data. So right now we've talked about data being open and accessible to everybody. We've talked about creating that data. So sensing that data, right, using sensors from satellites or from the ground or from the earth. Then we have the processing of that data. So from taking it from raw data to information, right? So by analyzing it in a specific way. Spreadsheets and databases are going to be our main 2 ways to do that. So things and data stored in columns and rows. We also have the concept of data entry, which means that we can either manually or programmatically import or augment that data. We use formulas to interact with these. So programs that you might be used to are Google Sheets or Excel. Yes, we still use those professionally. And next we have the ability to enter them into some database where we just interact or access those more programmatically. The next section we have up is harnessing data. So we can access data through something called an API. An API stands for an application programming interface, and it's just a way that allows users to access data and services over the web. There's many different formats that you can interact with APIs, in comparison to, say, a CSV or XML format, if you've ever heard of that. JSON seems to be one of the most common formats now. We'll get used to interacting with JSON formats. We can think of an API like a waiter at a restaurant where we're making requests, we're asking for food. The API is the waiter that takes our request to the kitchen and brings us back the actual data, and the food is our data in that example. There are some more nuanced concepts of free data access and ownership. These will be posted for us and for our reviewing pleasure after the presentation, because I'm a little bit short on time here. But it is important to think about who owns data and where this data access comes. So the tension between free access and ownership becomes particularly pronounced in cases of indigenous data, right? Or personal data. So if we're trying to use climate data from around the world, who owns the data that we get from the sensors in the rainforest, right? We don't own that land. That land isn't ours. Or when we think about personal data like 23andMe or like any of our health records, who owns that data and in what context are you able to use them? Something that I think is just very important to earmark for later if you're interested in. We also have the climate implications of storing data, right? Storing data is computationally expensive. It's energy expensive, which means that it takes energy to store data and then to access data. So one important thing to notice that's really relevant to what's happening right now, or prevalent that's happening to right now, is in the world of large language models and ChatGPT, especially for learners and especially for people who use large language models often, which I use them for work as well often, right? So every time you query a large language model like ChatGPT, I think you're using 10 times as much energy as a single Google search. And then it also uses 9 times as much water. So it's just important to keep in mind that all of our data, no matter where it's stored or how it's used, has some type of environmental footprint. So let's talk about the anatomy of a data project. If this was one thing to really focus on, or to come back to your computer and listen to me for a minute here, is this anatomy of a data project. So we have we have different ways that we want to think about our data, right? The backbone of almost every data-driven app or analysis that you're going to see is going to be very straightforward. You're going to get the data, you're going to clean the data, and then you're going to use it. So you're going to get the data somehow, you're going to clean it, right? Normalize it, put it in the right format, convert the numbers to the number you need them in, the dates to the date you need them in, reshape them in whatever way you need to, and then use it. By using it, we mean visualizing it, right? And we're going to call this extract, transform, and load. So I think a better way to shape this, and the way that I learned it, was to, step one should always be to frame the problem, right? So you take your general idea and frame the problem in the context of your data. Right? So how does the problem I want to solve, or the problem that I'm tasked with solving, how does that fit in with my data? Okay, well then step 2 should be, let's first get the data. Let's explore it, meaning let's look through it. Let's analyze it for trends. Let's clean it, convert it, reshape it if we needed to. Let's transform it in any way possible. And then preparing it means to visualize it or to look through it. So in these terms, you might also hear the term extract, transform, and load as an acronym for this, and that is the acronym that we should be keeping up with, right? So extract. This is where you get the data. It could be through an API like NOAA. It could be downloading a CSV from New York City's Open Data. It could be scraping values from a web page. In the example I'm about to show you, would be extracting daily temperatures from NOAA's API. Part 2, as mentioned, transformed. Once you have the data, you need to clean or reshape it in some way. That might mean renaming columns, filtering to adjust the date range that you care about more, converting numbers into formats that you can chart better, or Yeah, we'll leave it at that for now. I will say that this is often the transform step is often where beginners spend the most amount of time. And that is completely normal and that's completely okay. Learning how to change or to augment the data's shape or structure to have better downstream interoperability or to better view the data, I think is a really important skill to learn. And it's just something that you have to go through and you have to sit down and really understand your data. And then once again, the last section is loading it. That's where you do something with the data, right? It could be visualizing it, it could be analyzing it, it could be serving it through your own API or app. In the example I'm about to show you, we'll visualize some temperature trends. So you don't have to know everything at this part. You can just start with extracting and loading, or even using someone else's transformed data. But once you know this pattern of ETL, you can start building more complex and reusable projects. Also, this mirrors how most real-world tools work, right? Weather apps, delivery tracking, Instagram analytics. They all follow this type of pipeline under the hood. So if you can get used to doing this process for yourself, you'll have a really good time transferring that knowledge to actual app building, because those are how apps get built behind the scenes, right? They also extract data. They also transform it in their own way, and then they also load it in their own way. So before I pause for my last moments of questions, I'm about out of time here. Let me show you an example that I brought up for us. So if I switch my tabs, can we see my new tab in my presentation?
I'm looking at NOAA climate data Jupyter notebook.
Thanks, Michael. Okay, so what have I done here? So I'm using a Jupyter notebook. If we don't know what that is, it's not super important. Just think of it as a really quick way for you to get up and running with writing Python code. It has lots of built-in libraries specifically around data, right? So it is a really great tool to quickly interact with data. Just think of it like that. So what I'm doing here is I am extracting information using an API. So the API that I'm using is this API, which is one of NOAA's API. If you go to NOAA's website, you'll be able to interact with many of their APIs. If you go to access data, it'll give you more detailed instructions on how to make the API calls that I am making here. A lot of these are query parameters, just asking the API for specific things. And as we can see here, step one is always going to be to get the data, right? Like just very broadly is get the data. So I'm fetching the data. I'm fetching the data using a request and response cycle, as mentioned, and just storing my data from the response that we get. If you remember, the example that I used was that APIs are like a kitchen of some kind, where we, the client, the person, the user, asks for information. So when we ask for data, we ask the server, right? And the server is the one who goes back to the back of house to request and get that food. So they are, here we are fetching the data. So once I have this information stored into a variable, right? This is just programmatic from here. So what am I doing? I'm loading the data that I fetched from this NOAA API. I'm loading this into a pandas data frame, right? So a data frame in pandas. Pandas is like one of the premier Python packages for working with data. It has been for a very long time. It's a very mature package. If you're not familiar with what a data frame is, I would definitely take a moment to just spend a minute or two on Google looking through maybe what pandas is, or maybe use an AI to give you an overview of what pandas is and what a data frame is. You can think of it like a tabular data structure. So it has columns and rows in which you can interact with it. So then we did so if this is our extraction stage, right, which is just get the data, Then we have our transforming stage. So technically this would kind of be the transforming stage as well. So what I'm doing here is I'm transforming certain dates to a very specific date format. I am making sure that all values are numerically the same, or they're coerced to the same data type, so that they do not break my downstream use case for it. And then what is the next step, right? In that extract, transform, load section, when I was talking about loading it, right? We have to do something with it. We have to visualize it or analyze it. So we need to analyze it. Like when you think about analyzing, think about it as looking at the data, right? Like as human beings, you need to look at and understand this data for yourself before you can write an algorithm to do anything with it. So I use a lot of matplot library, which is just another Python library that helps you plot out data information. And so this is the plotting figure that spit out this chart, right? So this is a chart that tells us over this date, which is about a month. It's about 1 month long in 2023. Here's where the average high and low temperatures for the day. So this is a very, very straightforward extract, transform, load project. And I would like you to think about when you're going to work on some of this information, or when you're going to work on your hackathon. When you're going to work on your hackathon, think of this, right? So think of first, pick out a problem. Think, what do you want to solve? What are you interested in? There's many different ways to find out what you're interested in as well. You know, using like a GPT for a backboard to check ideas is a pretty good idea. Something that I often do as well. I've also included this link to Open Data, which has lots of open data sets for New York City specifically. They have everything from MTA information to rainfall to delays. So something like getting two data sets like the New York City rainfall data set and the subway delay data set, and graphing, building a dashboard to see if you could understand how those two pieces of data interact, I think would be a cool starting point. I've got a few other ones here. 311, so emergency phone calls. What time of day are there more or less of them, or maybe around like a holiday, maybe like around 4th of July. I know there's tons of noise complaints like over that weekend. So it might be interesting to try to plot that on a graph and see what insights you can raise from that data. They also have lots of information about trees and New York City parks information, even how many squirrels live in Central Park and what type of squirrels they are. So if you're like interested in animals and you want to build some visualization about like the types of squirrels with a heat map or something and where they live, I think that'd be interesting. And then there's also air qualities control using NASA, pollen and asthma risk by zip code, all through different open data platforms and information. I know that was a mouthful, everybody, so I'll make sure that I pause here to answer any questions you might have.
You know, I'm not sure if anyone can anyone unmute themselves? They might not be able to, but if you're able to add a question to the chat, you might be able to, if you can write something in the chat, we can answer it there.
And remember, I think they are able to unmute themselves, but you guys remember to ask questions to see how you can be able to use this for the hackathon, because this is a lot of great information that you can use for the hackathon.
Well, we do want to take a short break for anyone who needs to answer the call of biology. But after that, we'll give it 5 minutes, and then we'll start up with Steve and Jaret. But in the meantime, if you do have questions, just feel free to put them in the chat. All right, Patrick, thank you. And we'll start the break now, and we'll see you all in 5 minutes. Okay, so we are coming back. If anyone can hear me, if you've been on break, I hope you grabbed a nice little snack. And we are about to start the next session within the webinar. So I will leave it to our next guest, our presenter, to introduce himself. So Dr. Stephen Jaret, please feel free to take it away.
Thanks. I appreciate being part of this. So my background is I'm a professor of Earth and Planetary Sciences at Kingsborough Community College. And so what that means is I'm a geologist, interested in rocks, but rocks across the solar system. So Patrick gave us a really nice overview of data and sort of the approach and the data process. What I'm going to do with the next little bit is give us some case studies and examples of how we as planetary scientists use NASA data, and particularly data collected about other planets. So I'll just go ahead and get started here. Sure, what am I, screen? Ah, this one. All right, can everybody see?
Yes, looks good.
So I'm going to talk about sort of how we explore and deal with data from other planets. Just to give us an overview of what we're dealing with here, this is a not to scale version, but just a nice image that shows the various members of our solar system. I like this one because it includes the planets that we are all familiar with, but it also includes some of the smaller objects, particularly the moons of Jupiter, Saturn, Uranus, and Neptune, which also are important members of our planetary solar system. And I'm really going to be focusing on this planet here on Mars. But just to sort of set us, we as planetary scientists, or people who study the solar system, have been collecting data for a very long time. And this goes all the way back to Galileo. And I like showing this just to make the point that, you know, any kind of observation that we make is still data. And so even with primitive telescopes, Galileo was able to look out at, in this case, Saturn, and make drawings illustrating what he saw. And so that is certainly one kind of data. It's not just data are not confined to computers, but of course that's what in the modern world that is a lot of what we are dealing with. And so how we study the planets today are generally with spacecraft. And there's several different ways that we do this. The first is by sending spacecraft to other places. And one way we do that is we send it usually something with a camera or one of the other kinds of sensors that Patrick talked about before. Send that to a planet and it will fly by and just look out and collect and see what is there as it's flying by. More sophisticated missions will actually not just fly by once, but we can actually put spacecraft in orbit around the planet, which really allows us to A, get closer to the surface and be able to circle around and image the whole planet and image the whole planet over and over again. So particularly if you want to understand how surfaces are changing, it is important then to be able to see the same place multiple times over a long time period. We can also send spacecraft that actually land down onto the surface, and this can then have other kinds of sensors that need direct contact. So if we wanted to say, for example, measure the soil, or insert probes that measure temperature, that's something that you can do once you're on the surface having landed. And the most sophisticated of these are rover missions, where we actually deploy things that are anywhere from the size of a microwave to the size of a large SUV, that have on board various instruments and scientific tools. Essentially, these are SUV-sized science laboratories designed to drive around on the surface, explore different areas, and perform all kinds of tests and analyses. So what I'm going to talk about today is really an example of reflectance spectroscopy, which is one of the kinds of measurements that we make from orbiters. So this is an image of the Mars Reconnaissance Orbiter spacecraft that arrived at Mars in 2005 and had on board several kinds of instruments. And the one I'm going to talk about is this one shown here called CRISM, which is a compact reconnaissance imaging spectrometer for Mars. And you can see this is its size. This is not that big. It sits on a benchtop. Maybe it's the size of 2 or 3 shoeboxes. And that is the main instrument that collects all of this data. And the way this works is taking advantage of the way light interacts with rocks and minerals. The idea being that if there's some light hitting the surface, in this case, say sunlight, it interacts with the surface, and the light, the wavelengths, and the angles of that light that get reflected off the surface tell you about that material. Each kind of surface, each kind of rock on the surface will absorb light in a certain way or bend the light in a certain way, such that if you're flying your spacecraft over the surface of the planet and collecting light that is being reflected off, so this is sunlight shining on the planet and it bouncing off, and then your spacecraft can detect that, and we can use that to determine what kinds of things are on the surface. And we can do this in the lab as well. So here's an example of just a rock. In this case, it's a nice granite made of each of these different minerals, pink feldspars, gray quartz. And the atoms in those minerals are all bonded together in very specific ways. So you can see in this cartoon, there are several different styles of the way those bonds would vibrate in that crystal lattice. And so if you measure the light coming off of this surface, it's going to be dependent on how all these bonds are moving or the frequencies at which those bonds are vibrating. And so what you can end up getting, and this is shown here in this example, is what I affectionately call squiggly lines. But these are not just any squiggly lines. These are showing how much the amount of light being reflected at any given wavelength. So you can see exactly each of these bonds. You can convert that to a wavelength of frequency to see that, say, these peaks here would correspond to different kinds of vibrations. So you can do this in the lab and build up sort of a library of, okay, I know what pattern each mineral is, so then you can fly a spacecraft over a surface that's going to see a lot of different minerals on the surface and back out based on these lab studies. Okay, I know what patterns I'm seeing. So let's take an example again of CRISM, and this is again going to collect data that is the infrared wavelengths of light that are reflected off of the surface, having interacted with those minerals. And Patrick talked a little bit before about the get the data part. And so in the planetary world, we have this thing called the Planetary Data System, which is a NASA-run repository for data. All of the data collected from any of the NASA missions, because they are taxpayer-funded missions, that data is mandated to be open and free. The planetary world, I'm sure there are APIs and things, but for the most part, the APIs are not really well developed, and a lot of this is still in sort of FTP style, where you're actually going in and clicking through folder by folder. And I'll show an example of this in a moment. But I just wanted to give us a little bit of what this data looks like. So you can go to the PDS website, and these data sets, I think Patrick referred to this a little bit earlier, of geospatial. So what it means is you're collecting data while flying over the surface of the planet. So what that means is that for each data point, you're going to have some wavelength of light. In this case, our detector has 8 channels. So each of these represents a channel which is a specific wavelength, we're not able to collect across the entire spectrum of light because that would be too data intensive to send that back all the way from Mars. So to make the data smaller, we collect only in specific wavelengths, every so number. I don't remember the exact spacing, but there are 8 of these bands, and you then extrapolate in between. And so, but each of those is the wavelengths and how much of each wavelength at each position. And so that's what makes this a geospatial data, is that it's how much wavelength and location. So you're always tracking where that spot on the surface is. So I have here the website just as an example of what this would look like. And the data comes out, and here it is in its wonderfully boring structured format. And you can see each of these is a wavelength, and it comes in tab and spaced format. And for each of these, you would then see some amount of light at each wavelength. And if, when I'm done with this, if we want to come back, I can actually go to this website, and we can play around with like what it actually looks like to browse. In fact, let me do that. Am I still sharing? I don't think I'm still sharing. Let me go ahead and pull that up as well, just because I think it's kind of fun to see like the interface itself of what it looks like on that website. Okay, yes, got it. Here we go. Let's share. I'm going to share this window. Can you all see?
Looking at the targeted empirical record
Yes,
window.
perfect. Yeah, so here's one of those data sets. There are sort of web interfaces that have tools where you can sort of browse across the surface of the planet. Those APIs are not super great. So I'll just, for an example, so let's explore this data set. And this is the old school directory format. It does take a little bit of clicking around, but what's nice about all these data sets is they all have a README file where it tells you exactly what everything means. It tells you that we're looking at the TER data set. It tells you what all the file formats are. The README files are a super important part of being able to do anything with this data. But for an example, let's just go in and browse, and we'll browse in here, and we'll go to 2006, and let's just grab a file. And you can see it comes in a variety of formats. And in the header, the header, for example, would give you all this lovely information. Oops. The unfortunate thing about the way that PDS is structured is it tends to separate the X and the Y columns, in this case, the wavelengths and the intensities, into separate files. And so in that step that Patrick was talking about before about the transform, one of the most common things we have to deal with is putting and transforming it so that you can get X and Y in the same file. That makes it a lot easier when you're plotting things against each other to not have to read in data from 2 separate files. Why they don't automatically put them all in one file, I don't know, but that's where we are with the NASA world. So coming back to our presentation. So that's sort of about the data itself. Now let's take some examples here. So because what I really want to get across is like, what do we do with the data? What does it mean? How do we do something, get to that third stage, the load stage? So what I'm going to focus on is one example of an area on Mars called Jezero Crater, which is the landing site for the Perseverance rover, which some of you may have heard of. So this is it. This is an image. There are some color overlays, false color overlay on this, but this is an optical image base map showing this sort of delta-like sedimentary deposit area on Mars. And this is an area that was highly targeted with CRISM. And so this is one of those outputs. What you see here, this is the actual processed version of data directly off the spacecraft. And what you can do is, so you can now stack individual plots where within one study area, they show multiple different surface types. So for example, this red plot shows features that when we compare to our databases of minerals on the lab is a more olivine or sort of deep-seated mantle or mineral. Above that, we have the green, which show a mixture of silicate minerals and carbonate minerals, and really dominated by carbonate minerals, shown here. This is really cool because just from this alone, we can see that there are multiple different environments on the surface of Mars, which mean there must have had different environmental conditions over time. So you can start thinking about how did this form, why did this form, what was the interaction between the surface and, say, the atmosphere. Another thing we can do is we can take these data sets, and instead of just plotting squiggly lines, we can take that three-dimensional or two-dimensional data set and say, okay, I want you to make a map that says display in blue every place that has this blue pattern. Display in green every place that has this green. So you can actually make up these maps to really show that, look, oh, the divide in the minerals here is perfectly matched with the inner and outer edge of this crater. So you can start to understand the geology by processing the data and displaying it spatially and putting that together in sort of a multifaceted way. So with that, I know we have a little bit of time left, and I think we're going to have a demo of showing the visualization of this kind of data set using another kind of tool called OpenSpace.
Yes, thank you for that segue. And just before we proceed onto that, does anybody have any questions? Does anyone want to ask anything about the data sets that Stephen presented, or about the process, or anything else that that he just showed before we dive in further? Feel free to add something to the chat if you have a question. Okay. All right, so I'm going to share my screen, and hopefully this will work. So I am running off of, just to give everyone a sense of sort of like what we're about to see and how I'm using it. So OpenSpace is a project that was a collaboration between the American Museum of Natural History and a university in Sweden called Linköping University. They came up with what is basically the next generation of planetarium software to be able to view the known universe. This is currently in use at the Hayden Planetarium at the American Museum of Natural History. And NASA funded this with the intent of making it an open source piece of software for scientific visualization. And it contains and is regularly updating many, many different open data sets. So what we're going to see now is a view of the universe in real time. So let me share my screen. Can everybody see what looks to be a planet with some orbits around it?
Yes.
Okay, so we are looking at Mars, and we are going to be looking at a representation of Jezero crater, but you can also see in the background, there are many stars with many different levels of brightness and even different coloration. This is all real. This is not like some artist's interpretation. This is not an illustration. These are all real pieces of data that are being represented as they would exist in the universe in this position in space and time. So right now, this just to give you a sense of like how powerful this tool is. So I am just using, I'm using a gaming laptop. It has an NVIDIA chip in it, but it's an HP Omen 16 running Windows 11. So it's not like I'm using any kind of supercomputer to do this. It's just it does contain a very large amount of data and is very powerful visualization tool. You can import all different kinds of 3D models. You can put any kind of imagery in it. You can put any kind of Standard data, NASA has specific data formats and pieces of, or rather, things like a spice kernel is another thing that's known. It's this way of representing positions in space and time using this very structured data format, and it can use tools like Lua is a programming language, Lua. You can use it to create animations, just as if it were almost like a game development kind of setting as well. So what I'm going to do now is I'm going to fly in to Mars. So we're going to head towards Jezero Crater. And as we get closer, we are going to actually start seeing labels appear to show the features of the planet. So you are going to notice a bunch of different things. Like as we get closer, you'll see that there are these strips that are appearing, these sort of horizontal or rather rectangular shapes. And these are multiple data sets. These are data sets from a sensor tool known as HiRISE, which is responsible for using infrared detection to determine the distance, or rather the surface features of the planet. And it does it to a very high resolution. So, you realize we just came in from space and we just saw the whole, solar system and universe around it in space. But now I'm flying down to the surface of a planet, and now we're going to start seeing what it looks like to fly over Mars. So I'm going to land our camera onto the surface here into Jezero Crater. And I'm picking some really interesting features that are just kind of cool looking. So it seems sort of like flowing kinds of features. And as we get further and further, you can see that there is actually height in some of these features. It's not just a picture. We're actually coming in, and you can even see the altitude is sort of like listed here. So I'm currently a few kilometers above the surface of Mars. And I'm just going to I'm not the best pilot, so I'm still learning how to fly a little bit. But you can see there's some really interesting features that we're going to go over and check out. So let's get a little bit lower. Okay. And you'll also notice that, so of course, like I said, my computer is just a normal laptop. But as we move around a little bit further, you'll see that there are definitely features that are sort of coming into view or rendering as we go. So it's a lot of data that's being processed all at once. So you can see that the resolution of the HiRISE camera is sort of showing the features of the hills and gosh, my mouse is jumping a little bit faster than I want it to. Okay, so I'm just gonna scroll around a little bit so you can kind of see. Now there's the trails up in the sky of moons flying around Mars. I'm just gonna make those disappear. And then I'm gonna just sort of fly around a little bit so you can see, like, we're basically looking at the sides of the crater. So Stephen, I don't know if you want to do any narration for some of the features that we're looking at. I'm on the Perseverance focus. That would help if I switch to Mars focus. Sorry, I think that's why I was focused on the Perseverance model, and that's why it was being a little bit weird. So
you can see some ridges in the background, which are toward the edge of the crater. So you kind of create these high stand mountains on the edge of the crater. One of the things that I think is pretty cool is you see these sort of parallel ridges right here in the front. And these tend to be wind sculpted. So on Mars, there actually is atmosphere enough to sort of carve out these linear ridges just by wind. Sort of like dunes, but more linear in you have sand blowing on across the surface.
Just heading toward this little crater here, which I was flying over it before, and I noticed it has some of those interesting ridges within it.
Yeah, these are really common anytime you see loose sand, that you will get these. We call them yardangs. Inside the crater, you start to see these parallel ridges. And that's a very common feature. You see those also in areas with lots of loose sand, so like the high deserts of Patagonia, for example. You see those as well, or in places like Namibia as well.
So yeah, we get very close, and then you can start seeing that like it is getting a little more blocky looking, but this is still really good resolution. And of course, if your connection, I'm downloading a lot of this data also in real time. I have some of it locally saved on my computer, but I'm also as I'm going, if I fly to a new area, I'm getting new data. So one of the things that Stephen was showing before too was the CRISM imagery and data. And so what we're looking at too, and so I'm going to back out again just a little bit to show everybody. So we were looking at multiple, if those strips that I was talking about, like we could see, from high up. Whoops, let's go up. Phew. Hope nobody gets dizzy. So here you can see like the outlines, right? So these are different different assays or photos or images that were taken at different times of day, as orbiters are sort of like going around the planet. So the colors are not always going to match up when you're looking at many data sets all at once. But depending on, so one of the great things about OpenSpace is that these are all blended together. So we're actually taking multiple, the term I believe is photogrammetry, right? When you take multiple angles of photos and you combine them all together. So I'm going to just add another layer of color to this, which actually is going to come from the CRISM data. So let me see if I can remember which one it was. Let's see, I said it was, I should have noted this because now I'm trying to remember which exactly was this area. This guy, this guy. Just going to turn on a bunch of these layers and see what I can get. Because I know that one of them was right in this area. And it looked really cool on this section. I seem to be having an issue with the data load. Maybe it won't let me load multiple at a time. I'm just gonna back out a little bit so I can find where some of these data sets are coming in, but I know that the number of them were coming from Jezero. So we'll see them load up when they get selected. So here's like a higher view. Oh, here's one. I think this might be it.
Yeah.
Okay. So I have to do one other thing, which is to change it to add the colors in. So you can see it's already, so now we've added a new layer of image data, right, effectively. And I have to add a special command in OpenSpace. So one of the nice things about this is there is a online community, which people who are doing work and research or working in planetariums can actually help you with anything that you're doing. And that's actually where I got this CRISM data set. I was able to download it and just add it in manually to OpenSpace. Just 1 second. I just need to enter in a command. Oops, that's not the right one. Try that again. Copy. Paste. There we go.
Ooh.
I can tell that Stephen likes this. So now I'm going to come down and we're going to go in now in 3D to look at this as we come in. And I'm also going to change the opacity a tiny bit so that it blends in a little more with the surroundings. So now you can you still get a sense of the colors, but you're also seeing the 3D aspects of the features. It's coming down. Now it's going to take a minute, I think, to load some of this resolution. Turn the opacity up a little bit more.
Yeah, and this really allows you to see how the different things that visually look like they're different layers that are overlapping, they're different colors because they're actually different compositions, which is really cool.
Add some more mosaic. That might be. But yeah, so some of these colors, I think, can you give us a sense of like what the colors are showing us, Stephen?
The colors are showing different main composition of minerals, and off the top of my head, I don't know which color is which mineral, but it's basically telling you different rock types. So you can see that in this deposit, they're depositing different kinds of rocks in one area and then another. And off the top of my head, I don't remember what the colors correspond to, but it's a different one rock type or another.
Yeah, so if I turn the colors on just a tiny bit, we can see because it's actually, oh, that's right. I have to change the layer. Sorry. There we go. That's what's going to fix it. Right, there it is. Okay, I forgot a step. So if you change the layer, the color layer, it actually will allow you to see the features much better for the high rise 3D. So now you can actually, so now you're seeing this mineral composition that Stephen was talking about in these different spots, actually in the feature itself. So, you know, it's as if you have a Star Trek scanner and you can actually like scan the mineral and see like what it is from the surface if you were actually flying over it.
Awesome.
Get it really colorful. There we go.
Amazing.
Yeah, I like this feature the most because I thought, oh, this is like a cool plateau that's like in here, and it seems almost like volcanic, but it's got all these eroded parts and
Welcome to Mars.
very cool. So yeah, as I said, this is all free data. This is all stuff that anyone can download and run. I mean, I don't even think my gaming computer is a very high-end gaming computer. So it's you know, anybody can download this and play with it and learn to fly around. There's YouTube videos online to give you tutorials. We'll leave links to this as well so that folks can play with this. But again, you just have to figure out there's always open source tools out there that can help you. This is a case too. Like these data sets, these were already transformed for me. So just like Patrick was saying earlier, you can find transformed data and then you can just stick it into whatever tool you're using. We just happened to find here was a resource that was made available for us by the open source community in the OpenSpace project, and we can now blend it together and see, and compare it to the other visuals and data sets that Stephen was showing us earlier. All right, so I think I will leave it to Nate, and if anyone has any questions, again, like feel free to ask or to post here in the chat. And with that, I'll bid adieu.
Thanks, Mike and Stephen and Patrick. So yeah, I mean, that was awesome. I love the throughput too, kind of showing how you get the data, pull it in, how Stephen uses the data, and then seeing it actually in use. So, my only sort of wrap up is that like we like doing this stuff. We're trying to do more community events. Part of the reason that I got in touch with LaGuardia College was that we did an event at Civic Hall, which we share a space there. Yeah, so we're going to do more events throughout the year. The main Space Apps Hackathon is in October. So if you like this kind of thing, working with open data sets and especially interest in data from NASA and wanting to do cool visual projects with it, that's certainly the spirit of the kinds of things we like to do. I think, yeah, what we're going to do with this workshop is this is meant to be an open education resource. So we're going to collect the materials that you've seen as well as the recording and make it publicly available. So if you want to reference it or get any of the materials that were shared, we'll provide a public link, and then I'll try to get it to you. And yeah, hopefully we can, it sounds like, hopefully this gives you like kind of a good lead into your hackathon, thinking about, how to get sort of creative projects going, work with open data sets, think about the bigger picture around what kinds of data are out there. So yeah, that was kind of as far as we got. Amanda, are you still here? Do you want to say anything?
Yes, I am still here. I did have a quick question. If the students wanted to get in contact with you, with either four of you guys, just more of maybe help within, like maybe even the hackathon, just to try to get involved because they love the presentation and they love what they learned today. What are the best ways for them to get in contact with you, and would you be able to, like, I guess, put that information on, like, how can I share that information, or just the best way for them to get in contact?
I don't want to speak for everyone, but I'm happy to, you have my email, you can share it. And then, if other people have other ways of sharing their information, is there any sort of direct communication channel with the hackathon tomorrow? Like, do you guys have like a group chat or something?
Yes. And if, granted, I was going to say this so far, but if you four want to probably sneak peek and want to try to help them with that within the hackathon, I can give you the information on how you can pop in. But yes.
Yeah, I mean, no harm. I mean, I have meetings and stuff tomorrow, but if I'm available and somebody has a question and wants some direction, I'm happy to share. And yeah, it's also kind of our first time presenting this material, especially even as a group. So if it's helpful to get feedback, I think, and hear as we start to think about other types of content we want to do in terms of an event. We want to do more in-person type events and not just webinars, but yeah, it'd be great to hear from you guys as well. Not just what do you need from us, but also like what kinds of things would be interesting to see, or like future event ideas, things like that.
Yes, awesome. I'm looking forward to collaborating with you in the future. And students, please, they're putting their emails in the chat for a reason. This is a great way for you to get in contact with them, not only for the hackathon, but in many ways, right? Because this is a learning experience and you're trying to grow in your career. So remember, look at this as a great resource in order to help you grow. I'd just like to say thank you, thank you, thank you, thank you so much. This has been amazing. I've learned a lot of new things, and I'm like, oh, okay, that's cool. So I am excited. And that's all that I have. If you are, for the students who are going to be part of the hackathon, please, it is tomorrow at 3:30. Check your emails. It's starting tomorrow, but it's ending on Friday. It is a 2-day hackathon. So please, 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 feel free to come tomorrow at 3:30 in E500. I'm not answering any questions about the hackathon today. You will get all the information tomorrow, and I basically gave a lot of information throughout the last session. So I just want to say thank you so much to everyone who did attend. I really appreciate it. I hope you have a good day.
Thank you, Amanda.
Yes, thank you so much. And we will try to get this online with some resources if we can. But thank you all for attending.
Thanks, everyone.